Welcome to today's episode, where we're diving into the intricate world of database transactions with a spotlight on the essential concept of two-phase locking, or 2PL for short. As we journey through the complexities of transaction management, we'll explore how 2PL works, its two distinct phases, the challenges it poses, and the strategies we can employ to navigate those challenges. Whether you're a database administrator, a software developer, or just someone curious about how databases maintain their integrity and performance, this episode is filled with insights that will deepen your understanding. So, what exactly is two-phase locking? It's a vital protocol designed to ensure that transactions in a database remain consistent and intact. The process unfolds in two phases, the growing phase and the shrinking phase. During the growing phase, a transaction gathers all the necessary locks on data items. Think of it as the transaction building its resources to carry out its operations. Once a transaction releases a lock, it transitions into the shrinking phase, where it can no longer acquire new locks. This structure is crucial because it helps prevent conflicts between transactions that are happening at the same time. But it also introduces the possibility of deadlocks. Now, let's talk about deadlocks, which are a significant challenge in transaction management. A deadlock occurs when two or more transactions are stuck waiting for each other to release locks, leading to a complete standstill. To tackle this issue, database systems employ various strategies. One common method is to implement timeouts, which automatically terminate a transaction if it exceeds a certain wait time. Another approach is conservative two-phase locking, where all locks must be acquired before any operations can begin. While this can effectively prevent deadlocks, it may also reduce the overall concurrency of the system. Additionally, deadlock detection can be enhanced through the use of waits-for graphs. These graphs visually represent the relationships between transactions and the locks they hold, making it easier to spot cycles that indicate a deadlock. Transaction timestamps can also play a crucial role in determining which transactions should proceed and which ones should be rolled back if a deadlock occurs. As we continue, it's important to distinguish between locks and latches, as both are essential for data integrity but serve different purposes. Locks manage logical data integrity during transaction processing, ensuring that transactions don't interfere with one another and that the data remains correct. Latches, on the other hand, provide physical integrity for database structures during operations. They're lighter than locks and are held for shorter periods, which allows for greater concurrency. This distinction is key for optimizing performance, enabling databases to handle multiple operations at once without significant delays. Another interesting concept we'll explore is readers-writer locks. These locks allow multiple readers to access data at the same time, while ensuring that writers have exclusive access when they need to modify that data. This mechanism is particularly beneficial in scenarios where read operations greatly outnumber write operations, maximizing throughput and minimizing contention. As we delve further, we'll look at techniques for managing shared access to database pages. One method is the busy wait approach, where a transaction continuously checks for lock availability. While this can be effective, it may lead to wasted resources if not managed correctly. Alternatively, queuing algorithms can organize transactions more efficiently, allowing for smoother access. We'll also introduce optimizations like latch crabbing, which helps reduce contention during data modifications. This technique allows transactions to release latches as soon as they're no longer needed, freeing up resources for other operations and boosting overall performance. In this next segment, we'll focus on effective strategies for managing latches during database operations. A common scenario arises when a child page isn't found in the cache. In such cases, a transaction can either latch a future page or release a parent latch and restart the traversal process. While restarting might seem costly, it's infrequent and can be optimized by checking for structural changes in the database. We'll also touch on latch upgrading, where shared locks are initially acquired during traversal and then upgraded to exclusive locks only when absolutely necessary, particularly at the leaf level. This approach helps manage contention since multiple threads may compete for exclusive locks. Given that all requests pass through the root node, which rarely splits, optimistic latching can be applied here, significantly reducing the need for retries and enhancing efficiency. As we wrap up today's episode, we've covered a comprehensive overview of two-phase locking and its critical role in managing database transactions. We explored the phases of 2PL, the challenges posed by deadlocks, and the strategies to mitigate these issues. By differentiating between locks and latches, we highlighted their respective functions in maintaining data integrity. We also discussed readers-writer locks and various techniques for managing shared access to database pages, including efficient latch management strategies. Understanding these concepts is essential for anyone involved in database management, as they directly influence the performance and reliability of database systems. We hope this episode has provided you with valuable insights into the intricacies of transaction management. Join us next time as we continue to explore more fascinating topics in the world of databases.